All right, so for the last remaining weeks, we're going to start shifting into amines and biological molecules, but we've first got to finish chapter 23. Chapter 23 is all about amines, and we've got to do some basic nomenclature review. The one thing that people tend to mess up a lot when they're talking about amines are these two compounds. What's the one on the left called? What was it? Ammonia. What's the one on the right called? Ammonium. And because it's got that extra proton, that nitrogen has a positive charge, and we have to use the IUM prefix to indicate that it is a positively charged species. So anytime you see the IUM suffix, that indicates that that nitrogen has a positive charge. So there are a bunch of different nitrogen species. You can have a primary nitrogen species, meaning it only has one R group attached to it. You can have a secondary nitrogen species where you've got two alkyl groups. They don't necessarily have to be the same. You can have a tertiary nitrogen species, and all three of these can either be neutral or they can be their ammonium salts. The last one that we have is our quaternary ammonium species, and in this case this can only be the ammonium salt. Primary, secondary, and tertiary amines can be their ammonium salt under acidic conditions, or they can be neutral under basic conditions. So it really depends on the pH. The other term that gets thrown around a lot in this chapter is an alkaloid. Does anybody know what an alkaloid is? An alkaloid is an amine that's derived from a natural source. So amines are common in biological chemistry, and they're important in a lot of pharmaceutical or recreational drugs for that matter. So amines derived from a natural source. So if you think about like nicotine from cigarettes, that's an alkaloid, right? It's an amine derived from a plant source. Amines have really simple reactivity, and we're going to learn a few new reactions, but we've seen some already. And let's put a little review tag here. The first thing that amines can do is they can act as bases, right? So if we treat this with an acid source, all we're going to do is protonate our amine. We know amines aren't very good acids, but they're relatively good bases. And when you do this, you form your ammonium salt, whether or not that's a primary, secondary, or tertiary amine. The other reaction that we've seen with amines is where we treat it with something like methyl iodide, where we know that amines can be either good bases or relatively good nucleophiles. So if we do this, we can actually get a quaternary ammonium salt where the conjugate anion is iodide. So alkylating amines is very common as well. What's the shape of a neutral amine? Does anybody remember? If we're looking at this guy, what's its geometry? Trigonal pyramidal. However, anytime we look at the quaternary salts or the ammonium salts, we're looking at something that is just normally tetrahedral, right? The interesting thing with amines is that they'll flip inside out like umbrellas. So that lone pair on one side of the amine will actually do something called electron tunneling and randomly appear on the other side of the amine through this weird quantum mechanical phenomenon. And so you actually can't get chiral amines. It's impossible. However, if you look at the periodic table, below amines you have phosphorus and then all the way down to arsenic. The further down you go through the periodic table, the harder it is to do that umbrella flip, and you can actually get chiral phosphine complexes and arsenic complexes. But amines are so small, the electrons will actually tunnel through, and it just does this rapid inversion at room temperature. The only way to stop that would be to theoretically cool it down to close to absolute zero and then freeze it into that trigonal pyramidal shape. Does that make sense? A little bit weird. If you go into P-Chem, you might talk about that more, but we're not going to even touch that in this class. All right, we'll briefly talk about nomenclature. Nomenclature for amines is similar to alcohol nomenclature. But instead of an "all" suffix, you get an amine suffix. This is one of the easier functional groups to name. So let's take a few easy examples. What would this be called? Ethylamine. Yeah, please don't miss this one. So ethylamine. So instead of ethanol, we just switch the suffix to amine. What about something like this? Yeah, isopropylamine.
So we use the substituent name, not the base name.
Say that again?
So ethylamine would be a substituent ethyl, not a,
So the amine is going to be the root in this case because it's the highest priority substituent. So another way of naming this one on the right, for example, if you go through and number this, you could say, well, that's 1, 2, right? Counting out from the amine. So you could call this 1-methyl ethylamine. That would also be appropriate, but it's basically replacing the "all." So it's not that the isopropyl is a substituent.
but with all, it's ethanol. Ethanol, not ethanol.
So shouldn't that be ethanol?
Yeah, I mean, that's, yeah.
That's a good question. Nobody really calls it ethanamine. I think just simply because it doesn't flow right. Ethylamine's just easier to say. I'll have to look into that, though. That's a good point. And then if we look at something like this, we know that cyclohexanes have pretty different nomenclature. This would just be cyclohexylamine. So yeah, I guess for simple amines, you can treat the alkyl group as a substituent and just call it methylamine or ethylamine. All right. The other thing to pay attention to is if there's a higher priority substituent, you'll actually refer to the amine group as an amino substituent, but in this case, the amine is the highest substituent. So let's do a simple example. Let's do this compound. If we go through and we number it, are we going to go 1, 2, 3, or the other way? Probably the other way to minimize our priorities, right? So if we go through, we go 1, 2, 3. That way the amino group is coming off the lowest priority position. So this will be an amino. So for example, if we were to name this, this would be 1 amino 2 propanone. So let's make a little note of that. if a higher priority functional group is present, then an NH2 group is called an amino substituent. Does that make sense? So the ketone's higher priority than an amine, so that's going to take precedence when you're talking about the suffix for -one here.
What's the next one up from the priority list?
That's a good question. So if we go back to our priority lists, I think we talked about it in the ketone chapter. So if we look at it, hydroxy's higher. We've got aminos all the way down here. So thiol, an alcohol, a ketone, an aldehyde, a nitrile, an amide, an acid chloride, an ester, and a carboxylic acid are all higher priority. To be perfectly honest, I just want you guys to remember that carbonyls are a higher priority, right? Because those are always going to be our highest priority functional groups. I'm not going to get nitpicky and be like, well, you didn't realize that a mercapto group was higher priority than an amino group. That's kind of getting into the nitty-gritty of things. All right, so let's go back to the amines. And I'll do some practice here. Yep.
Can we do an example with like 3 R groups off the amine?
Yeah, we'll do that next. Let's do some practice ones, and then we'll work through them. So that's a methyl group. And the next one, oops. We've got an ethyl group, an amine, and a fluorine. And the last one we'll do our tertiary amines. All right, so here's 3 examples. First thing I do anytime I see a molecule with stereocenters is before I even name it, I just identify the stereocenters, right? So if we look at this stereocenter, is that R or S? S, exactly. So we've got an S stereocenter here, and then what about right there? R. All right, so we've got our stereocenters defined. Next thing we need to do is identify the longest carbon chain, which is going to be that straight chain backbone. But should we number it going left to right or right to left? Yeah, left to right. We want the amino group to be at the highest, or sorry, lowest possible number. All right, so now if we go through and we name this, this would be 3S, comma, 5R. So we bracket in our stereocenters at the beginning because we have 2 of them and we have to number it. And then we've got a 5-methyl. And then 3-heptan. And then our suffix will be amine. So 5-methyl 3-heptanamine be the full formal name of this. What about the next one? What would the parent be? Aniline, right? So if we look at this parent group right here, we're quite familiar with from the previous chapter. We've got an aniline derivative. Should we number going counterclockwise around the ring or clockwise? Counterclockwise. So in this case, we go 1, 2, 3, 4, 5, 6. Can we use ortho, meta, or para when naming this? No, because that's only used for difunctionalized. So if we look at this, would the ethyl or fluoro go first? The ethyl, right? Due to the alphabetization? Have to do the alphabet song in your head. A, B, C, D, E. So 5-ethyl, 2-fluoroaniline. So we don't have to worry about stereochemistry, just numbering our substituents on the benzene ring. All right, now the one that Chloe was asking about, what do we do if we've got multiple substituents coming off of a nitrogen? Do you guys remember when we were naming amides and I said you have to do an NN prefix? We do the same thing here. So if we look at this, we've got an ethyl group coming off here. We've got an ethyl group coming off here. So this would be N, N, diethyl. So you want to name those substituents. If you had a methyl group, it'd be N, N, ethyl methyl, and then you would name the rest of it. But in this case, we've got 2 ethyls. We'll just call them a diethyl. And then if we number it, we go 1, 2, 3, 4, 5, 6, 7. Do we have to worry about stereochemistry? No. This was something I tried to drill into your head first term, but we've got symmetry through this molecule, right? There's no stereocenter in it. So if we go through and we try to number this, this would be NN diethyl 4-heptanamine. Does that make sense? All right, so that's as far as I'm going to get into naming. You can go pretty crazy once you get into natural product alkaloids, but to be perfectly honest, once you get into big, crazy alkaloids from natural products, people just refer to them by their drug name or by some arbitrary name that's not at all related to IUPAC naming. All right, let's take a look at a little bit of review for preparing amines. So we'll do a little bit of quiz work here. So let's say I want to go from here all the way to the amine. So we've got an alkyl halide. We need to install one more carbon and we need to get an amine off of there. How can we do that? Sodium cyanide. So we know sodium cyanide. We'll do SN2 chemistry with alkyl halides. We'll pop on that cyano group. That means we'll get our nitrile intermediate. And then how can we convert our nitrile to an amine? Yep, LAH, so we can reduce it and then treat this with acid. So we can reduce that nitrile pretty easily to an amine. So we saw that in our carboxylic acid derivative chapter. Let's do another one. Let's say I want to go from the carboxylic acid to the amine, and we're not going to gain or lose any carbons for this example. How can I convert a carboxylic acid to an amine? I'll give you a hint. This first one's 2 steps. Yeah, socyl chloride. Thionyl chloride. So remember I said whenever you're stuck, convert your carboxylic acid to an acid halide, and then how can we get that nitrogen installed? Yeah, NH3XS. So now we can get to our amide, and then how can we lop off that CO double bond and get to our amine? LAH. It's the same reaction as above. And you can get to your final product that way. All right, let's do another bit of review. let's say I want to work with benzene and I want to get an amine to come off of benzene. So we're trying to go from regular benzene to aniline. What reagents do I need to accomplish this transformation? Yep. So first reaction is similar to what we did in lab. We need nitric acid and sulfuric acid. That gives us our nitrobenzene. And then how can we reduce that nitro group to an aniline? What was it? Yeah, zinc and HCl. Or iron and HCl, so zinc or iron. Whoops. You can also do catalytic hydrogenation, so you can do this with H2 and platinum. That also works. Really, just about any reducing conditions will reduce that nitro group to an aniline. So that's review. And then preparation of substituted amines. So all of the amines we saw in that top portion were all primary amines, meaning they only had one carbon substituent coming off of it, but we can make substituted amines. So for example, if we've got ammonia, we can treat this with methyl iodide. We know the lone pair will attack the methyl group. It'll kick off our iodide. And we can get to, oops, our salt. So this would be our primary ammonium salt. And then if you've got any other ammonia around, this ammonia will come deprotonate. And you can get to your primary amine. One thing I don't know if I brought up, but we see methyl iodide in a lot of these alkyl halides used in the Klein textbook. They're really nasty to work with. If you think about your DNA and your proteins have a lot of amino groups coming off of them. If we're dealing with methyl iodide in lab and you spill it on your hands, it's going to start adding methyl groups onto your DNA and protein. That's really, really bad. That causes cancer in a severe way. And so scientists are trying to avoid the use of methyl iodide because it's a really, really bad thing for chemists to work with. The other problem is as soon as you form this, you will also end up over-alkylating it. And it's really, really hard to stop at just one alkylation. So what this is called when you end up at your quaternary ammonium salt is exhaustive alkylation. Normally chemists aren't looking to exhaustively alkylate something, and the reality is that this is not synthetically useful for primary amines. So it'll usually overshoot and give you your quaternary amine. Does that make sense? I'll show you guys some other routes, though, for making substituted amines that are a lot more environmentally friendly and a lot more useful. Is it okay if I skip pages? All right, I'll wait a second. How many of you guys have heard about the giant airbag recall? A few of you guys? Yeah, so I think almost like a third of all cars on the road have had their airbags recalled in the past few years. So pay attention to your car and check the mail because your airbag might be recalled. And this is very relevant to the next reaction. The next reaction is called an azide synthesis. And the overall reaction uses something called sodium azide, where if you have an alkyl halide, you treat it with sodium azide, which is NaN3. When you do this, you end up forming this intermediate. Let me put in all the lone pairs just so we can keep track. You end up forming an azide. Why do you think these might be useful in an airbag? It's probably going to decompose and shoot off N2 gas, right? So azides are sometimes used as propellants. It also means that they're explosive. However, sodium azide is pretty acutely toxic, and they found with some of these airbags that they didn't so much blow up the airbag as explode the airbag, which doesn't help too much when you're in a car accident. If you want to convert this to an amine, you can do it pretty easily by either hydrogenating it, so we can use H2 and platinum, or we can use lithium aluminum hydride followed by water. The main driving force for this reaction is always going to be that production of N2 gas, though. So let's take a look at the mechanism for this. So the first step we said is, reaction with our alkyl halide. And sodium azide is a salt that looks pretty unstable, and it is unstable. What will happen is this will just backside attack, kick off our leaving group. Now we've got our azide intermediate. In the next step, we're going to treat this with lithium aluminum hydride, so just a hydride source. And this hydride is going to attack this nitrogen and then kick up electrons onto this nitrogen. Okay, and then in the next step, this lone pair will clamp down, form a nitrogen-nitrogen triple bond, and kick electrons over to the nitrogen. So we'll blow off nitrogen gas. Oops. And then in the next step, we're just going to treat this with water to give us our neutral amine. So this is a nice way of forming a primary amine. Yeah. This is a pretty old school way of making amines, but it's pretty reliable if you're doing a simple synthesis. The one main problem is you're going through explosive intermediates. So if you were to do this on an industrial scale, your boss would laugh at you. The other thing too is sodium azide's really bad for you. So again, it's one of those reagents, if you get it on your skin, it's going to cause some serious problems. So a lot of alternative routes have been developed to avoid the azide synthesis. The main alternative that's very popular is called the Gabriel synthesis. So the main advantage to the Gabriel synthesis is it avoids explosive azides and toxicity problems. So let's take a look at the overall reaction. It's not a very green reaction in terms of atom economy because you're using this big, bulky reagent as your starting material. This is called phthalimide. And in the first step, we're going to treat this with potassium hydroxide. What do you think will happen if we treat this with potassium hydroxide? Where do you think the most acidic proton is? On the nitrogen, right? So we just spent a whole chapter talking about alpha carbon chemistry. In this case, the proton coming off of the nitrogen is unusually acidic because it is in between those two carbonyl groups. So we form essentially a resonance stabilized anion. The next thing we're going to do is alkylate it. So we'll treat this with Rx, which is just going to be our alkyl halide. And then step 3, you can treat this with H3O+, and I'll put a little note that this is slow. Or you can treat it with rocket fuel, which is hydrazine. This is fast. Normally when you go through the Klein textbook, you'll see the hydrazine variant just because it speeds up the reaction times considerably. When you do this, you'll get your primary amine, where that R group is the R group from your alkyl halide. And then what you'll end up with if you use acid is your dicarboxylic acid, and I'll put if H3O+ is used. And let's make a little note for what we get if we use hydrazine. And you get this if H2N and H2 is used. So depending on that last step, you'll get 2 different byproducts out of this. So let's go through and try to figure out how this mechanism works. Sorry, this should be shown as a more clear single bond. Oop. All right, so we said the first step is going to be deprotonation of our phthalimide. So we've got hydroxide around. This hydroxide will just rip off this proton. That'll give this nitrogen a negative charge. Nitrogens normally really don't like to have a negative charge, but in this case it's resonance stabilized. And we'll treat this with our alkyl halide, which was step 2. So we'll attack, kick off our leaving group. And then in the next step, we've got the 2 routes, right? We've got one with H3O+, and what will acid do to an amide? It'll just hydrolyze it, right? And convert that amide to a carboxylic acid. So we saw that in a pod a while ago. So if we do that, get phthalic acid, and then we get, our amine out. So that's one option, and we said that this is a slow reaction. It normally requires a lot of heat to bust open an amide. However, if we use hydrazine, we get a similar reaction where we'll ring open the system, pop out our amine, and this is a much, much, much faster reaction. Does anybody know why this reaction is so much faster? Well, let's think about nucleophilicity too. What's more nucleophilic, a nitrogen lone pair or an oxygen lone pair, and why? Think about which one's holding its lone pair more tightly. Is it going to be the nitrogen or the oxygen? Oxygen. Oxygen's much more electronegative. It's going to hold its lone pairs close to itself, where the lone pairs on hydrazine are much more available for a nucleophilic attack, which accelerates this reaction tremendously. So these are very useful for reactions. Oops, sorry. That should be just an NH. All right, maybe we'll just end it there today. Tomorrow what we'll do is we'll talk about reductive amination, and we'll do a little bit of practice with synthesis. One thing to warn you guys about is the next couple chapters, we're going to be covering material pretty quickly, so make sure you do sapling starting today. So try to knock out as many sapling problems as you can. Once you get to a point where the reactions don't look familiar anymore, you can stop. And then we'll cover that new material tomorrow. But try to get a jump start on it.